Now back to some concept. Suppose we had a function defined parametrically like this. So let's say that x is equal to x of t and y was equal to y of t. And suppose that we took this function and revolved it around the x-axis. You can probably see what that would look like. Some earn. Okay, now when I revolve it, this would be like this at the end. Okay, so that's what it would look like if we revolved it around the x-axis. The question here is, can we develop a formula for the area of that surface? Suppose that you took some scissors and you sliced the surface and unraveled it and stretched it really tight. Well, then your shape would look something like this. Now again, this is stretching it really tight. Then we would get a rectangle. It's not truly a rectangle. See, these are little increments here that are stretched, otherwise they would be curved in nature. So this here represents a length, which is going to be this length here. Alright, so what is the area of a rectangle? Well, the area of a rectangle is this length times this height. But this white height, what is that corresponding to in this diagram here? Do you see that this white is this white here? It's going to be this white over here. Do you see that these are the circumference? So the distance from here to here is the circumference. Now, again, this is a bit of a stretch, no pun intended, for this rectangle. Actually, some of the circumferences would be a little bit larger than others, or a lot larger. But think of these as little gauze strips here, where each one has a blue length, but has a height of the circumference. And the area of the surface would be the sum of these area of gauze strips. So that would give us S would be the infinite sum from A to B. The height would be 2 pi times radius, because circumference is 2 pi times radius. But what is the radius? The radius is the distance from here to here. Hopefully you can see that in the blue. How do I represent that radius? Well, that's going to be the function y of t, the distance from 0 to the curve. So this is going to be y of t. So that gives us a circumference. Now I need the length of the curve, and the length of the curve is just a good old-fashioned dx dt squared plus dy dt squared dt. So if you take a function, let's say this purple function, and revolve it around the x-axis, the area of the surface is this. It's 2 pi r heights times the distance of the gauze strips make up the surface area. So that will lead us now to the final example, example number 5. Please try it. And do this one by hand, work it all the way out, see if you get the answer, and we'll discuss the solutions in a moment. Okay, take a moment to walk through the solutions with me and see if you got 8 times pi squared. Now, that's the surface area of the shape. But what is the shape in words? Can you figure out what shape this makes and a common day item that has this shape? Well, let's see. If I take x squared plus y minus 2 squared, well, then that's going to give me the cosine squared t plus the sine squared t, which is equal to 1. So that means I have x squared plus y minus 2 squared equals 1. That's my original parametric equation, which gives me not a function, but a circle. And that circle has a radius of 1 and a center at 0, 2. So we take this circle, 0, 2 is the center, a radius of 1, and we rotate that about the x-axis. What shape does that make? Are you thinking donut? Because that's what I'm thinking. Although the donut is spelled do-nut, not like Dunkin' Donuts. And I'm going to say yummy. And that is the end of lesson